Dmitri Mendeleev, Order in the Elements. Russia, mid-19th century. On a long, cold journey between provincial towns and St. Petersburg, a young chemistry professor is traveling with a suitcase full of samples and a head full of half-formed ideas. His beard is wild, his hair is uncooperative, his clothes slightly frayed. He has just finished a massive textbook on chemistry and he is exhausted. But there is one thing he cannot stop thinking about: the elements. There are more than 60 known by now: hydrogen, oxygen, carbon, metals like sodium, potassium, copper, and zinc, halogens like chlorine and bromine, each with its own properties, its own quirks, its own combining ratios. Chemistry students memorize them as a list. He hates lists. He wants pattern, a deeper order. His name is Dmitri Ivanovich Mendeleev. He will eventually give the world one of the simplest, most powerful diagrams in all of science: the periodic table. But for now, he's just shuffling cards. Mendeleev's path to this train is not smooth. He is born in Siberia, in Tobolsk, the youngest of many children. His father, a headmaster, goes blind. His mother runs a glass factory to support the family. It burns down. She takes young Dmitri on a long, hard journey west, hoping to get him into a good school. He makes it to St. Petersburg, studies, becomes a chemist. He works in European labs, returns to Russia, and teaches. His lectures are lively, sometimes chaotic. He's known for arriving in the lab without a tie, code flapping, but with a mind that sees connections others miss. As he prepares his chemistry textbook, he runs into a problem. He needs to present the elements in some logical order, not just alphabetically. Atomic weights have become reasonably consistent thanks to decades of work: Lavoisier's balances, Dalton's atoms, Avogadro's invisible counting, Canizzaro's clarifications. But when he lines elements up by increasing atomic weight, the properties don't increase smoothly. Instead, similar behaviors seem to recur in a kind of rhythm. Lithium, sodium, potassium, all soft, reactive metals, combining in similar ways. Fluorine, chlorine, bromine, iodine, all sharp-smelling reactive non-metals. He suspects there is a periodicity lurking in the list. He needs to see it. So, he writes each element's name, atomic weight, and key properties on separate cards. And he plays. Picture Mendeleev at his desk in St. Petersburg, cards spread out like some strange kind of solitaire. On each card, an element's name, its atomic weight, its typical valence, the number of bonds it tends to form, its known compounds. He starts arranging the cards in order of increasing atomic weight, left to right. But instead of making one long line, he wraps to the next row when properties start to repeat. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Then the next row: sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. Patterns emerge. Soft, highly reactive metals line up in one column. Hard, lustrous metals, the transition metals, gather in the middle. Non-metals and halogens form their own groups. When something doesn't fit, he moves cards around. He adjusts some atomic weights he suspects are wrong. More dramatically, when he sees that a property pattern suggests an element should exist in a slot where none is known, he does something bold. he leaves the slot empty. He predicts that nature has an element there undiscovered. He even estimates what it will be like. He calls them Eka elements, using the Sanskrit Eka for one beyond. Eka boron, Eka silicon, Eka aluminum. He writes down approximate atomic weights, densities, oxide formulas, chloride formulas. It is a strange mix of rigor and audacity. Out of this card game, Mendeleev distills a principle. If you arrange the elements in order of increasing atomic weight, their chemical and physical properties recur periodically. He phrases it as a periodic law. In his first tables, atomic weights is the guiding variable. Later, others will realize that the deeper parameter is atomic number, the number of protons in the nucleus, but Mendeleev doesn't know about the protons yet. Still, the pattern is strong enough that he trusts it more than some measurements. When tellurium and iodine look out of order by weight but fit better by properties, he places them in the order the pattern demands. When an element's reported atomic weight doesn't fit the group it seems to belong in, he suggests the weight is wrong. He publishes his table in 1869 in a Russian journal. At first, it is one of several attempts at ordering the elements. Others like Lothar Meyer in Germany have noticed periodic trends too. But Mendeleev's version has something special. It is not just descriptive, it is predictive. Prediction is where a pattern becomes a law. Within a few years of Mendeleev's publication, experiment catches up. In 1875, a new element is discovered in a zinc ore. It has properties remarkably close to what Mendeleev had predicted for Eka aluminum. Light, low melting, forming a trichloride and trioxide with the right densities. It is named gallium. Later, scandium and germanium are discovered, matching his predicted Eka boron and Eka silicon with uncanny precision in atomic weight, oxide formulas, and densities. Each filled gap is like a chord resolving. Skeptics begin to take the table more seriously. It looks less like a clever filing system and more like a map of something real. Mendeleev refines his table, adds new elements as they are discovered, adjusts groupings. He does not get everything right. He has no noble gases yet. Those will arrive in the 1890s and slide into a new column at the far right. He does not know why the periods have the length they do. Electron shells and quantum mechanics are far in the future. But the core idea holds. The properties of elements are not random, they are structured, and that structure can be laid out visually. It is easy to reduce Mendeleev to a bearded face in a textbook, floating above a grid of boxes. The man himself is more complicated. He is known for his stubbornness, his untidy appearance, his long hair and beard that make him look older than his years. He writes and speaks bluntly, sometimes annoyingly so, on matters of science and education and policy. He works on topics outside pure chemistry. The Russian oil industry, the strength of vodka, the need of standards and reforms. He teaches generations of students, arguing that chemistry must be useful, connected to industry and agriculture, not just theory. He lives through political shifts, struggles with institutions, occasionally falls out of favor. He's not a saint. He's a working scientist, a teacher, a citizen, with biases and blind spots. What endures is the way he turned a messy heap of facts into coherent structure. Before him, elements were like words in a disorganized dictionary. After him, they are characters in a periodic story. The periodic table is more than classroom wallpaper. It tells you at a glance which elements are likely to behave similarly and which are not. It tells you that sodium, potassium, and cesium will all form +1 ions and violent reactions with water. That fluorine, chlorine, and bromine will all be hungry for 1 extra electron. That elements in the same column share valence patterns because their outer electron structure, although Mendeleev didn't know the electron story, are similar. It hints at what kinds of compounds are possible, which alloys, which salts. Later, when quantum mechanics arrives, the periodic table becomes a test and a triumph. Schrödinger's equation and Pauli's exclusion principle, applied to electrons in atoms, explain why the table has its shape. Why the first period has 2 elements, the next 2 periods 8, then 18, then 32. Why there's that awkward F block, the lanthanides and actinides, usually dropped below like a footnote. Mendeleev did not know about orbitals or spins, but his table anticipated their consequences. He drew the pattern. Later, physics filled in the mechanism. Once you know which elements exist and how they are arranged, another question becomes natural. How do these elements actually connect? What does it mean physically for carbon to bond 4 times? Why does oxygen typically make 2 bonds? What shapes do molecules have? The periodic table is a catalog of ingredients. The next big puzzle is the recipes and the structures they form, especially in organic chemistry. There, carbon chains and rings build up an enormous zoo of molecules: alcohols, acids, sugars, dyes, poisons. Chemists in the 19th century have formulas that tell them how many carbons and hydrogens and oxygens are in a compound. C6H6, benzene. But they don't yet know how those atoms are arranged in space. Straight chain, branching tree, something else? One German chemist, in particular, will wrestle with this puzzle. He will propose that carbon atoms link together in chains. He will stare at the formula C6H6 and feel that something more symmetrical is hiding there. And, as the story is told, he will have a half-waking vision of atoms dancing and a snake seizing its own tail, a ring. His name is Auguste Kekulé. In our next episode, we'll sit with him by the fire as he dozes and dreams, and we'll unpack what it really means to say that a molecule has a ring structure. We'll talk about how the idea of a hexagonal benzene ring, alternating single and double bonds, opens the door to understanding aromatic compounds, dyes, pharmaceuticals, and the entire architecture of organic chemistry. If Mendeleev gave us order in the elements, Kekulé will show us how those elements can loop back on themselves, turning lines into rings and formulas into structures you can almost picture.